Very nice welcome. A very nice welcome to the Bharatiya Kisan Krisak Farmer Quantum Physics class or quantum classes. And in previous chapter, we learned about the uncertainty principle. Now see this uncertainty principle with some examples. So first is example is to calculate order of natural width delta nu of the line emitted by an excited atom with average lifetime of 10 to the power minus 8 second. So here we use the uncertainty principle to calculate. The order of natural line width is uh, equals to delta nu equals to 1 by 2 pi into delta t equals to 1 by 2 pi into 10 to the power minus 8 hertz, or delta nu equals to 1 by 2 pi into 10 to the power 8 hertz equal to 1.67 into 10 to the power 7 hertz. Next question. Calculate the lower limit of energy of an electron in atomic nucleus if the atomic nucleus is 5 into 10 to the power minus 15 meter. So solution. The uncertainty in electron position delta x is given equal to 5 into 10 to the power minus 15 meter. Hence delta p, the uncertainty in momentum, must be greater than equal to h cut by delta x, or greater than equal to 6.26 into 10 to the power minus 34 joule second divided by 2 pi into 5 into 10 to the power minus 15 meter. After calculation, this value is 2.11 into 10 to the power minus 20 kg meter per second. So here from these examples we see that next we should here calculate the energy. The momentum also be of the same order if this is uncertainty in it. This suggests that the kinetic energy of the electron is far greater than its rest energy, and we can write kinetic energy equals to Pc greater than equal to 2.1 into 10 to the power minus 20 kg meter per second into 3 into 10 to the power 8 meter per second using this value, and which comes out to be greater than equal to 6.33 into 10 to the power minus 12 joule. So kinetic energy equals to in electron volt 39 mega electron volt. Thus the kinetic energy of an electron must be greater of 39 mega electron volt for it to be a nuclear constituent. But experiment shows that the electron in an atom have only a fraction of this energy. So we conclude that electrons cannot be in atomic nuclei. That is, the electron is out of the nucleus. So we see this uncertainty principle with some examples. So with this example, what we calculated, here we should understand that the theoretical limits set by uncertainty principle have nothing to do with the accuracy of the measuring instrument. Even the most sophisticated instruments shall be limited by the uncertainty principle. This concept was found difficult to accept by many leading scientists like Albert Einstein. Hence, a number of thought ideal experiments were proposed and debated in the Solvay held at Brussels in 1950 to disprove the above principle, but without any success. The analysis of some of the thought experiments illustrate very well the physical implication of this uncertainty principle. Therefore, we discuss them briefly in this lecture. Now see some thought experiment. Thought experiment. We discuss here some thought experiments that help us understand the uncertainty principle. All these attempts reflect a search for a way of highlighting this principle. In this direction, they seek to determine the position and momentum of a microscopic particle to an arbitrary accuracy. So here is a thought experiment to disprove the uncertainty principle and see what comes out to be after this thought experiment. Measurement of the position of an electron, the first thought experiment, the measurement of position of an electron, that is the gamma ray microscope, with gamma ray microscope. Let us consider a conceptual experiment first discovered by Heisenberg, which attempts to measure the position of electron as accurately as possible. This experiment consists of an arrangement in which an electron is illuminated and its image is observed through a microscope as shown in figure. Microscope. Electrons travel in the direction of the positive x direction in the form of a well-defined monoenergetic beam. That is, the velocity of the electron is known exactly. The position of an electron can be located by observing the light, that is photons, scattered by the electron into the microscope. Clearly, the precision with which the position of electron can be determined is equal to the resolving power of the microscope. Thus, it is equal to the minimum distance by which the microscope can resolve two objects, that is, given by delta x equals to lambda by sine phi. Here lambda is the wavelength of the photon used to observe the electron, and phi is the half angle subtended by the aperture of the microscope at the position of the electron. This result is a standard result from optics. Thus, to obtain as accurate a position measurement as possible, light of short wavelength must be chosen, such as gamma rays. Now, in order that an electron be observed, it should scatter at least one photon into the microscope. In the process of scattering, the photon would transfer momentum to the electron, causing it to recoil. For instance, if the photon is scattered by 90 degrees, the momentum imparted to the recoiled electron along x direction would be equal to that of the incident photon, which is equal to h by lambda. But the photon can be scattered at an angle between 0 degree and phi. Hence, the x component of its momentum after scattering can lie anywhere between 0 and p sine phi, where p is its momentum. Since momentum is conserved, the magnitude of the electron's recoil momentum along x direction is uncertain by the same or a greater amount, that is delta x into delta px, greater amount, that is delta p sub x greater than equal to p sine phi equals to h by lambda sine phi. Hence, the product of the two uncertainties is delta x into delta p sub x greater than equal to h, that is multiplying this equation, value of delta x and delta p sub x, which is consistent with Heisenberg's uncertainty principle. It is evident that by taking lambda small enough, that is by using gamma rays, delta x may be made quite small. This, however, would increase delta p sub x such that product of delta x and delta p sub x is always finite and given by the uncertainty relation. To gain further insight into the uncertainty relation, next we see one of the most famous of these thought experiment, that is the single slit diffraction experiment, in the next lecture.